I'm just watching a piece of documentary footage of Professor Andrew Wiles talking about how he felt when he was solving Fermat's last theorem or proving Fermat's last theorem, and he's saying like it was the most important moment of his working life, and it was just the most simple, beautiful, elegant thing that just seemed to fall exactly into place, and it was just he's almost in floods of tears when he's talking about it, and that's how I feel about my ideas, some of them. This quantum gravity idea that I've come up with. That's genuinely how I feel about it. I think it's just such a simple, elegant, easy to understand solution. It was everything that I really wanted it to be as a scientific conjecture or scientific theory or hypothesis or whatever you want to call it. I yeah, I just everything fell into place when I made this one assumption that gravitational fields or electron densities. I can see the gravitational field around the electron density of an atom. There's the electron density that we can see, then there's the electron density that we can't see, just beyond that, and that's creating the atom's gravity, the atom's gravitational field, right? And then applying that to stars, planets, galaxies. I mean, it's ephemeral, very invisible, very hard to detect, or maybe not that hard to detect, cloud of electrons surrounding, say, an object like the Earth. And yeah, it reflects light. Got that down, of course, because it's electrons. It can transmit doubly particles between the nuclei of other atoms incoming to the electron field, the electron cloud, and yeah, between the electrons and the electron cloud and the atomic nuclei of an object approaching. And so it can keep, for instance, the moon in orbit around the Earth that way by a coin I termed, a term I actually coined, gravito-electroweak interaction. I don't think that there had been anything known as the gravito-electroweak interaction in physics, to the best of my knowledge, on any search engine before I'd coined the term. So, I mean, if nothing else, I get to my credit, I think, for posterity, having coined the term gravito-electroweak interaction or gravito-electroweak theory. And hey, maybe that's all my job has been as a physicist, philosopher of physics, whatever you want to call me, whatever I get to call myself without a degree, because philosopher, anyone can call themselves a philosopher, obviously. You don't need a degree in philosophy to call yourself a philosopher, obviously. Some of the greatest minds in the history of philosophy never had degrees in philosophy, obviously. David Hume never had a degree in philosophy, Jesus, but so many didn't. And okay, I'm no physicist then. If I need a PhD in physics, call myself a physicist, which is a type of philosopher, obviously. But I'll call myself a philosopher of physics then. I think what I'm trying to do is derive something that's teachable, that's physically meaningful for most people, a sort of philosopher slash reporter of science. And then I can get into like philosophy and say, oh, I'm a natural philosopher, and that's almost back to physicist again. Or say, that cosmology is a branch of philosophy, which traditionally it is, of course, and go back to physics that way via cosmology, or go to mathematician via logician, since Bertrand Russell and Whitehead forged this grand union between philosophy and logic. Sorry, mathematics and logic. And now via the Langlands program, we're forging this relationship between geometry and number theory via representation theory and group theory and so on. And that'll forge, I reckon, like psycholinguistic connections. I reckon the work of Ed Witten will be very important and all that and so on. So, I mean, yeah, however ineptly or adeptly, what I'm doing is philosophy, most certainly. It pertains to physics, obviously, and why not call it, therefore, the philosophy of physics? It most certainly is that, if it doesn't deserve the title physics as such. Then we draw all these distinctions, and who really cares? I don't. What I care for is the discovery. The ideas themselves are so enticing. It gives me such energy. It gives me such drive and momentum. And joy. It really gives me such great joy, and it's such a huge struggle. And he's talking about the beauty is suffering is the title of the video, and it's on a great YouTube channel I think I'm going to subscribe to just now, called A Study of Everything. And yeah, the beauty comes out of suffering. If you suffer earnestly long enough and hard enough for anything in life, understanding of this or that theory in science. I think you will gain great benefit out of doing so, out of the endeavour in doing so. And I think what I've discovered is worthwhile. What I've been conjecturing is a perfectly legitimate approach to quantum gravity, and a perfectly sound bit of scientific conjecture, or perhaps theory, hypothesis. Is it possible to disprove? I guess if we discover some string theoretic gravitons, then it would be disproven. Of course, if string theoretic gravitons don't just turn out to be photons. But no, like simple, elegant, easy to teach, easy to understand. Yeah, yeah. It'd be so abstruse. It'd be so lost in mathematical complexity and topologies and compactification of infinite dimensions in spaces and all this sort of stuff, and group theories and special orthogonal Lie groups and octonions or whatever it is next, and this mathematization and abstruseness. No, it all needs to come down to a diagram and something you can really show to people. Yeah, something you can draw, really, I think, in physics. Feynman diagrams, Penrose diagrams, diagrams. And it's a great grand hunt after truth and beauty and elegant ideas. And I think I found something elegant, dare I say, something beautiful, something that works well, something that requires us to abandon a few of our assumptions, or quite a lot of our assumptions really, such as antimatter. I think it causes us to redraw the standard model without the antimatter in it, but adumbration, shortening, removing of assumptions that we don't need, Occam's razor and so on, remove the unnecessary assumptions, makes it more beautiful, makes it more elegant. Minimalism, style, simplicity. Because the standard model is a bit hulking, isn't it? It seems a bit arbitrary, some of it, and it seems a bit clunking and creaking, and like they always want to add more particles into it, like gluinos and neutralinos and squillinos, whatever they are. The next new particle for particle physicists to salivate over, whatever it is they love doing with particles, licking them or whatever it is. But no, when it comes to Andrew Wiles, whatever, I think I know some of what that is. I know what he's feeling when he's talking about his mathematical work with Fermat's last theorem. Yeah, I've experienced that in my life. I'm glad to have experienced that in my life. I mean, that's one of the most important things that's ever happened to me. And yes, like he said, one of the most important things in my professional life, my working life, as a writer of philosophy, if you like, a philosopher. It changed my life forever when I discovered that almost 8 years ago now. Actually, when I was in France with my grandmother at her house, preparing to sell it, and just doing a few odd jobs here and there, painting walls for her and whatnot, preparing to sell it, I came up with this. Well, I had this eureka moment when I was looking through an old A-level physics textbook that I illegally downloaded from Pirate Bay, among many other bits of physics literature that I'd accumulated here, there and everywhere. Just having to read popular science books by Feynman, the Theoretical Minimum series by Susskind, and all sorts of stuff online. Wikipedia, yes. MIT OpenCourseware, yes. All stuff put up by universities, real research papers that isn't Wikipedia, but Wikipedia is perfectly reliable and a great starting point, I think, for a lot of knowledge. Endless YouTube videos about physics, science, quantum theory, etc. Yeah, it coalesced on something. It coalesced on this Debye-Lesage model. Like this new mechanical ether, and the idea of ether never really left us, even in general relativity, even in contemporary particle physics. It's never really departed our understanding. The left side of my face, there's always been a problem with it. I think I've got Bell's palsy or something. Maybe it's from not understanding Bell's theorem. That's a bad joke, but yeah, it's always been a bit not quite right. Not as reactive as just doing my eyebrows now. Not as reactive as my right side. Oh, have I got hypochondria really? I don't know. Anyway, yeah, I think I've understood something. I think I've got a novel idea in physics. I'm still no mathematician. I don't think I ever will be. I use mathematics when I need it, when I need to calculate something, and I'll use equations when I need to calculate something. But I generally don't think in terms of mathematics. And I actually credit that kind of inclination with my ability to have come up with this idea, since there's an inordinate amount of mathematical talent being thrown at this problem in theoretical physics. Huge numbers of people whose mathematical abilities are way beyond where I'm at. And that's been the case for about 70 years on this problem, and it hasn't really progressed very far. So that in itself, I think, is a clue that it would actually be someone with less mathematical facility who would end up solving it. Because you run the experiment right for so long, quantum gravity hasn't been discovered. It hasn't coalesced on anyone's understanding, really. Or the community hasn't agreed that anyone's been right about it yet. So you run the experiment for X number of decades with high amounts of mathematical talent, great degrees of mathematical talent thrown at it. It seems like that's not the answer to solving it then. Maybe the answer is with less mathematical talent, but perhaps some physical intuition and enough mathematical ability and enough ability to express what I mean, in writing at least, and enough of an ability to, if nothing else, draw the interactions and do diagrams of the interactions that I'm describing. So I fail to see really how I'm not a physicist, and I fail to see really how I haven't produced physics. Because physics is philosophy, etc., etc., and I'm a philosopher, I'm a natural philosopher. So yes, Andrew Wiles, I really know where you're coming from. Thanks for that video. Study of Everything, it's a great video.